Welcome to this fourth episode of the podcast, The Pump Zone, presented by Pump Systems Academy, powered by Dynapro pumps. Did you know that empty microscopic vapor bubbles can actually violently explode with, enough force to shatter solid industrial steel?
Yeah, it sounds like science fiction, but it is completely true.
Right. So today we are taking you inside the brutal physical environment of pumping systems for this deep dive. We've pulled together a whole stack of engineering research, metallurgical articles, and your own listener notes.
Yeah, we really wanted to figure out the exact mechanical and chemical properties that, decide whether a pump survives its job or just completely self-destructs. Because it is a really delicate balance to strike.
Exactly, because a pump isn't just, moving fluid from point A to point B.
No, not at all. The internal components are constantly enduring just intense mechanical stress, massive temperature fluctuations, and complex chemical reactions.
So to understand why pumps fail, let's look at the sheer physical stress they endure day in and day out. You have continuous rotation, sudden starts and stops, massive dynamic loads.
Right, which puts a tremendous strain on a material's tensile strength.
And that's how much pulling force it can take before tearing apart, right?
Exactly. That and its yield strength, which is basically the point where the metal bends but won't snap back to its original shape. That continuous cyclical action is where fatigue really sets in.
Because a solid metal shaft might easily support a massive static weight.
Yeah, but in a pump, you have an impeller spinning like thousands of times a minute. That cyclical loading, just bending and unbending the metal over and over, causes these microscopic cracks.
Wow.
Yeah, even if the stress stays safely below the material's elastic limit, meaning it can still flex and bounce back, millions of those tiny flexes will eventually cause that solid metal shaft to just snap.
Okay, let's unpack this, because there's a huge trade-off here when we talk about surface wear. It really reminds me of a smartphone screen.
Oh, that's a good comparison.
Yeah, you can engineer glass to be incredibly hard so it resists surface scratches, which is, like resisting abrasive wear in a pump.
Right.
But making it that hard often makes it brittle.
Right, it loses its toughness.
Exactly. It loses its ability to absorb a sudden impact. So the moment you drop that hard screen, it just shatters.
What's fascinating here is how physical properties, like heat, complicate that exact trade-off.
How so?
Well, if your highly wear-resistant pump casing lacks good thermal conductivity, it just cannot draw the heat away from the friction points.
So the heat just gets trapped inside the metal.
Yeah, and when metal traps heat, it physically expands. If engineers haven't meticulously accounted for that thermal expansion, the moving parts actually swell up.
Oh, and close the gaps between them.
Exactly. You lose your critical clearances in the seals in the casing. The components literally grow into each other.
That sounds bad.
It creates extreme friction that completely locks up the machine.
But even if you build a pump robust enough to handle all that heat and physical flexing, the fluid you're pumping might just eat it from the inside out, right?
Oh, absolutely.
Yeah.
Imagine combining two different metal alloys in a pump that moves an electrolyte fluid, like, say, salt water.
Okay.
You have unintentionally built a battery.
Wait, a battery inside the pump? How does that even work?
It's called galvanic corrosion. So the salt water acts as a bridge. One metal acts as the anode, meaning it readily gives up its electrons.
Right.
And the other metal acts as the cathode, pulling those electrons away. That constant electron shift literally dissolves the weaker metal over time.
And while it's dissolving, you also have abrasive wear from suspended solids, like sand scraping the surface.
Yeah, and erosive wear from high-velocity fluid slamming into the volute.
Which is that spiral casing wrapped around the impeller. So the pump is just getting attacked physically and chemically from all sides.
Exactly.
Well, here's where it gets really interesting. Going back to the hook about bubbles.
Yeah.
Looking at the research notes on wear mechanisms for this deep dive, I actually have to push back on this. How can bubbles destroy industrial-grade metal? They're just air.
Well, that's the thing. They aren't air. They are vapor.
Vapor, yeah.
When the local pressure inside the pump drops drastically, the fluid physically boils at room temperature.
Oh, wow.
And that forms these vapor bubbles. Then, when the flow sweeps those bubbles into a higher pressure zone, they can't sustain themselves. They don't just pop, they implode violently. This is cavitation.
So we're talking about microscopic implosions right against the metal surface.
Yes. Each collapse generates a high-energy microimpact, almost like a tiny hammer striking the metal. Over time, millions of these shockwaves literally blast away microscopic chunks of the surface.
That is wild.
And fighting this requires that perfect balance we mentioned earlier.
Hmm.
Extreme hardness might protect against abrasive sand, But if the material lacks toughness, it shatters under those cavitation shock waves.
Right. So what does this all mean for you listening? It means material selection is never about finding one, like perfect super property.
No, not at all.
It's about mastering a really delicate, high-stakes compromise between mechanical strength, chemical compatibility, and wear resistance.
Exactly. If we connect this to the bigger picture, it really highlights how every single engineering choice is a negotiation with physical forces. You fix one vulnerability, and you might accidentally expose another.
Absolutely. But before we go, consider this. If cavitation vapor bubbles hold enough explosive kinetic energy to blast apart solid metal, could future materials be designed not just to resist those microimpacts, but to actually absorb and harness that kinetic energy?
Now, that is a fascinating thought.
Something to think about next time you hear a pump running. Be sure to tune in to the next episode of The Pump Zone, presented by Pump Systems Academy, powered by Dynapro pumps.